Welcome to Study Loop.
For the first part, the total power is the power input from the battery, and that power P is equal to the EMF epsilon times the current I. And this is equal to epsilon times, if we expand the current, we can write it as the peak current I naught into 1 minus E to the minus R over L times T. And this is epsilon squared over R, since the peak current I naught is equal to epsilon over R. And this is multiplied by 1 minus E to the minus R over L times T, where R is the resistance and L is the inductance. And we know these values to be 6 volts whole squared, so 6 for the EMF, and the resistance is 8 ohms into 1 minus E to the minus, and again we substitute our values, that's 8 divided by the inductance of 2.5 henries, all multiplied by T. And so in the simplest form, this power is 4.5 watts multiplied by 1 minus E to the minus 3.2 per second times time T. And so we have an expression for the power delivered by the battery. And secondly, we want to calculate the rate of dissipation of energy through the resistor. So that's the power through the resistor, PR. And this is defined by I squared times R. And again, we can simplify as we did above. This is epsilon squared over R into 1 minus E to the minus R over L times T. And that's squared. And again, we can substitute our values in here, and we find that this is, again, epsilon squared over R is 4.5 watts into 1 minus E to the minus, and we get, again, R over L to be 3, not 0, but 3.2 per second multiplied by T, and all this is squared. And hence we have an expression for the power dissipated through the resistor. So finally, the rate at which energy is being stored in the inductor we'll call PL. So the power through the inductor is equal to I multiplied by the EMF, which is L di dt. And we can do as we did before. So I is epsilon over R into 1 minus E to the minus R over L times T multiplied by L times di dt. So if we differentiate the expression for I above with respect to time, we get epsilon over L E to the minus R divided by L times T. And if we simplify this expression, we get that this is epsilon squared over R into E to the minus R over L times T minus E to the minus 2 R over L times T. And again, if we substitute our values in like we did before, we get this to be 4.5 watts multiplied by E to the minus 3.2 per second times T minus E to the minus 6.4 per second, which is 2 times the value the previous bracket, times T. And then we have an expression for the rate at which energy is being stored in the inductor. But finally, we can note that if we expand the square in part B, then parts B and part C add to give part A. So that means the total power is equal to the power across the resistor, answer in part B, plus the power across the inductor for answer in part C. And the total power delivered is dissipated in the resistor and the inductor, and the conservation of energy requires that this is so.